Welcome to Slow Science Sleep, the channel that explores science in a way so calm it might just make you forget you have a brain. Today, we're diving into the deepest mystery imaginable. What really happened before the Big Bang, before time, space, and that cosmic explosion that birthed everything we know? But before we wander into the theoretical mist, thank you for tuning in. We're sorry in advance if this keeps you awake rather than helping you doze off. Please like, subscribe, and drop a comment sharing where you're watching from and what time it is over there. Now, let's float into the void where everything began by not beginning. The Big Bang, as a term, is misleading. Suggests a noise, an explosion, a start in some fixed spot like someone igniting cosmic fireworks. But in truth, the Big Bang was more of an everywhere all last once expansion. Not a localized event. Around 13.8 billion years ago, everything, space, time, matter, erupted from a state of unimaginable density and temperature. We call it a singularity. Not because it was unique, though it was, but because our laws of physics break down at that point. And that makes physicists deeply uncomfortable, in the same way someone might feel when trying to explain why they can't describe anything before 0 seconds on the universe's stopwatch. But here's the kicker. What if that wasn't the true beginning? Before we reach back past the Big Bang, we must clarify what it means for something to be before an event that created time itself. Time is not just a background actor. It's a construct that emerged with the universe. Asking what came before the Big Bang is like asking what's north of the North Pole. You might feel clever for asking, but the answer still disappoints. And yet, theoretical physicists are not easily discouraged. They chase pre-Big Bang ideas like archaeologists, hunting the ruins of a temple beneath layers of rock that don't officially exist. Some propose that the universe is cyclic. It didn't just pop out of nowhere. It's been doing this forever, or at least long enough that the idea of a first universe becomes meaningless. The concept is as poetic as it is disturbing. Big Bang, expansion, slow death, big crunch, repeat. A cyclic model suggests that our universe is just the latest phoenix in a cosmic cycle of death and rebirth. This idea traces back to ancient philosophies, but has been polished with 21st century science. Roger Penrose, a Nobel laureate in physics, proposed a theory called conformal cyclic cosmology, or CCC for short, because scientists love naming things like their top-secret government projects. In CCC, the far future of our universe, when all matter has decayed, and black holes have evaporated, transforms into a state that becomes indistinguishable from the ultra-hot conditions before the Big Bang. At this point, a new universe begins. The arrow of time continues, but the universes are like beads on an infinite string. Each one is distinct but mathematically connected, like fractals in cosmic embroidery. Then we have the ekpyrotic model. This one throws in extra dimensions and two massive branes. Yes, brains, not brains, floating in a higher dimensional space. Our universe exists on one brane, and every few trillion years, it smacks into a parallel brane, unleashing a new Big Bang. Think of it as cosmic tectonic plates colliding, except instead of causing earthquakes, they create all of reality. And you thought parallel universes were only for sci-fi fans. The ekpyrotic model avoids the singularity problem by turning the Big Bang into a transitional moment between phases of cosmic contraction and expansion. Time, in this view, never actually begins. It just cycles through stages. The branes themselves have always existed in the higher dimensional bulk. So asking what came before is like asking what came before branes started dancing their slow, graceful smash. Another idea worth entertaining is that our universe emerged from a quantum fluctuation in a pre-existing vacuum. In other words, from nothing, but not the kind of nothing you get when you clean your room and find no snacks. This is quantum nothing, a simmering froth of virtual particles popping in and out of existence. In this model, a universe like ours could spontaneously arise due to quantum mechanics driven by a tiny fluctuation that snowballed into everything. Now, this idea gets philosophical very quickly. What is this quantum vacuum? Is it really nothing, or is it a sea of potential? The quantum vacuum is like a magician's hat that looks empty but hides infinite rabbits. In some models, this vacuum is eternal, producing bubble universes continuously. Ours is just one of them. These bubble universes form what's called the multiverse, an ensemble of universes with different physical laws and constants, floating like soap bubbles in a grander cosmic bath. If true, then the Big Bang wasn't the birth of all things. It was just the start of our local cosmic neighborhood. There might be countless other Big Bangs, each igniting in its own pocket of space-time, with its own rules and histories, some of which may be deeply weird. Imagine universes with no gravity, or where time runs backward, or where your socks never get lost. Of course, we can't visit these universes, not because our passports wouldn't be accepted, but because they're causally disconnected from us. No signal can cross the boundary between universes, making the multiverse hypothesis virtually untestable. And in science, untestable means uncomfortable. Still, many cosmologists find it appealing because it explains fine-tuning. Our universe has just the right ingredients for life, not because it's special, but because we couldn't exist in any universe that wasn't. Then there's string theory, which gives us another narrative. In string theory, particles are not point-like objects, but tiny vibrating strings. And the universe has more than the 4 dimensions we know. Some versions propose 10 or even 11 dimensions. The extra ones are curled up so tightly we can't detect them. In this framework, the Big Bang might be the result of a transition in the configuration of strings or branes. It's like the universe tripping over its own shoelaces and landing in a whole new reality. Loop quantum gravity offers a different lens. In this theory, space-time is not continuous but made of discrete loops. It quantizes gravity the way quantum mechanics quantizes everything else. Some models suggest that a previous universe collapsed and then bounced, giving birth to ours. This is the big bounce scenario. Instead of a singularity, we had a crunch followed by a rebound. According to some loop quantum cosmology models, the bounce occurred around 13.8 billion years ago, but there was a contracting phase before that. Now you might ask, how would we ever know which theory is right? Can we ever see beyond the veil of the Big Bang? Surprisingly, some physicists believe there might be signatures, tiny irregularities in the cosmic microwave background. The afterglow of the Big Bang might hint at events that occurred before it. For instance, Penrose's CCC model suggests that we might detect concentric circles in the CMB, relics of black holes from previous universes. These are speculative, controversial, and hard to verify. But they show that cosmologists are not content with saying we don't know and leaving it there. So what happened before the Big Bang? It depends on which theoretical hat you wear. If you're a fan of cyclic time, the universe has always been cycling. If you like branes and extra dimensions, maybe we're living in the aftermath of a higher dimensional fender bender. If quantum fluctuations are your thing, then perhaps the universe is an accidental masterpiece painted by chance. And if you're philosophically inclined, perhaps the question is meaningless, and that's the answer. What's undeniable is that the Big Bang isn't the end of our questions. It's the beginning of our curiosity. And the deeper we dig into what might have come before, the more we're forced to confront the limits of our understanding. But those limits are precisely where imagination begins to shimmer like distant starlight on the edge of time. Long before the first particles formed, before space curled into geometric patterns and light began its ceaseless sprint across the cosmos, There was a boundary beyond which our instruments, our equations, and even our imaginations begin to tremble. The moment we reach that frontier, the so-called 0 point, we encounter not just a physical limit, but a philosophical one, because what lies before time? What substance is there without distance? And how does one discuss origins in the absence of anything at all? To begin navigating that conceptual wilderness, we must approach the nature of time itself. In most cosmological models, time is not independent from space. It is stitched to it, forming the flexible, ever-shifting tapestry we call space-time. The Big Bang didn't just expand matter into pre-existing emptiness. It brought space into existence. It generated time. This means that before the Big Bang might be as nonsensical as asking what's inside a shadow. Not because there's nothing, but because the question defies the shape of the object itself. Still, rather than surrendering to linguistic deadness, scientists have attempted to work around the problem. If our universe is but a moment in a larger cosmological story, then perhaps we can gather clues by studying what came immediately after the Big Bang. That first fraction of a second, where everything changed more rapidly than in all the billions of years that followed, is the best fossil record we have for the conditions that preceded it. One of the key ideas here is inflation. Not the economic kind that makes groceries more expensive, but cosmic inflation. A period of exponential expansion that supposedly occurred in the first trillionth of a trillionth of a trillionth of a second. During this fleeting interval, the universe swelled from subatomic to cosmic proportions. Like a balloon suddenly filled with air from a hose set to ludicrous speed, inflation explains why the universe looks so uniform in all directions. But the question that always follows is, what caused inflation? What triggered it? And what was the nature of the space, if any, before this growth spurt began? This is where quantum fields enter the picture. In inflationary theory, a hypothetical field called the inflaton field permeates the early universe. This field was responsible for the rapid expansion. When it decayed, the energy released reheated the universe and gave rise to the particles we know today. But if fields like this can exist and behave this way, then maybe the inflaton was active in a space beyond our visible universe. Maybe its fluctuations ignited multiple universes, each beginning with its own inflation event. This leads us again to the idea of the multiverse, not as science fiction, but as a direct mathematical consequence of the inflationary model. The multiverse isn't just a backdrop for speculative storytelling. It arises in models like eternal inflation. Here, inflation doesn't stop everywhere at once. Instead, different regions stop inflating at different times, forming isolated bubble universes. Ours is just one such bubble. Outside our bubble, inflation might still be occurring, creating new bubbles endlessly. It's a bit like boiling water. Each bubble is a universe, and the pot is the inflating spacetime. In such a scenario, the Big Bang isn't unique. It's a local event, the birth of our observable universe within a much vaster and more diverse reality. But this raises a strange idea. Perhaps there never was a singular origin point. Maybe the cosmos has always been bubbling. Of course, this leads to more abstract questions. If there's a multiverse, where is it? Not in our observable space, that's for sure. Multiverses exist outside our cosmic horizon, beyond the reach of any light signal, telescope, or microwave detector. In other words, they may be mathematically valid, but permanently invisible to us. A conundrum, because science prefers things it can test. Still, many scientists are content following the math wherever it goes, even into unobservable realms. But not all models are quite so committed to eternal existence. Some take a subtler path. Quantum cosmology, a field that applies quantum principles to the entire universe, suggests that time itself might emerge from a deeper, timeless state. This is a strange but profound idea that before the Big Bang, there was no ticking clock, no sequential order, no before and after. Instead, there existed a quantum potential, a mathematical cloud of possibilities, all coexisting in a timeless sea. When conditions were right, the universe tunneled from this potential state into classical existence. This process resembles quantum tunneling, where a particle passes through a barrier it seemingly shouldn't be able to. Here, the entire universe tunneled into being. In Stephen Hawking's no-boundary proposal, the universe doesn't begin with a singularity, but with a smooth transition from a timeless, spaceless quantum realm into classical spacetime. Think of it like the South Pole. There's no point south of the South Pole because all directions from it go north. Similarly, the universe might have no boundary in time. It just curves smoothly into existence. No bang, no boundary. Just emergence. This idea is elegant but hard to picture. We like beginnings. We want cosmic fireworks, drama, noise, light. But the no-boundary model suggests a gentle birth, a quiet emergence from a quantum blur. It's the cosmological version of waking up from a dream without realizing when sleep began. Now, it's worth noting that we have no direct evidence for any of these pre-Big Bang models. They exist as mathematical constructs, elegant and consistent within their frameworks, but unconfirmed by observation. Still, they serve a purpose. They remind us that our current understanding of the cosmos is incomplete, that the Big Bang is not an answer, but a question mark with fireworks around it. And speaking of questions, here's a strange one. Could our universe be a simulation? It sounds absurd, and yet some physicists entertain the idea that all of reality, space, time, particles, laws, might be the product of a computational process. If this were true, then the Big Bang could be analogous to a boot-up sequence. Time begins when the system initializes. The singularity is just the first data point. Simulation theory has no evidence to support it, of course, but it raises fascinating philosophical issues. If our universe is a simulation, then it's embedded in a reality we can't access. The before becomes an entirely different ontological realm, like the space behind your television screen when you're watching a movie. You can't enter it, you can't affect it, but it's real in a way that makes your reality feel borrowed. Regardless of whether we emerged from a brain collision, a bouncing loop, a quantum field, or a digital grid, all these theories share one thing: they challenge the finality of the Big Bang. They turn it from a hard wall into a doorway. And though we can't step through it yet, we can lean our minds against it and listen. Interestingly, even the cosmic background radiation, once thought to be the final whisper of the Big Bang, might contain hints of something more. If inflation occurred, it would have left behind a specific pattern of gravitational waves, ripples in space-time that move at the speed of light. Detecting those waves could tell us about the exact mechanisms at play in the first trillionths of a second. And perhaps, if we're lucky, even earlier echoes. Experiments like Biek's and Planck's satellite have tried to capture this information. So far, the results are inconclusive, but the pursuit continues, because even the faintest signal from before the beginning would reshape everything we think we know. For now, we remain on the shoreline, scanning a dark ocean, aware that the waves we see began in the middle of a mystery. But the fact that we're even asking what came before time, what birthed the space we float in, is a sign that curiosity burns brighter than any supernova. In the end, maybe the question isn't whether the universe had a beginning, but whether beginnings are the right way to think about reality. Maybe everything simply is, not as a line, but as a web, a mesh of potentialities with the Big Bang as one brilliant spark caught in a storm of eternal physics. If there's one constant in the human effort to understand the cosmos, it's that every time we believe we've found a foundation, it crumbles into a deeper mystery. The Big Bang was once that firm foundation, the singular starting point. But now, it's increasingly viewed as a curtain, behind which a more complex, older, and possibly eternal stage might lie. To peer behind that curtain, we have to shed not just our tools, but sometimes our intuitions. Intuition works well on human scales. We understand the arc of a thrown stone, or the cycle of a day. But pre-Big Bang physics does not care about human scale. Logic. It stretches our reasoning into dimensions and timeframes that resist comprehension. Imagine trying to picture a time before time, or a size smaller than any definable length. It's like trying to fold origami with fog, and yet the theories persist. One such theory is based on the idea of holography, not the kind with lasers and floating images, but the holographic principle in physics. It proposes that all the information within a volume of space can be described by the data encoded on its boundary. Like a hologram, a three-dimensional image generated by a two-dimensional surface. Our universe may be a projection from a lower-dimensional reality. This idea becomes especially intriguing when applied to the Big Bang. Some cosmologists suggest that the Big Bang might not be a beginning at all, but a transition of encoded information from one-dimensional state to another. The birth of space-time as we know it could be the moment the data on a cosmic boundary unraveled into a holographic expansion. This view doesn't require a bang, just a shift, something like pressing play on a cosmic projection reel. Another path to explore is the possibility that our universe is part of a statistical ensemble. In this view, space-time and particles are not fundamental, but emergent properties arising from entangled quantum states. In such a scenario, what we perceive as the Big Bang could be analogous to a phase transition, like water freezing into ice. The universe crystallized from a chaotic quantum soup into structured space-time. Before that moment, the universe existed, but without the form or order that would allow beings like us to even define existence. This concept can be traced to ideas in quantum gravity, where space-time emerges from the entanglement of underlying quantum bits, units of information, not matter or energy. As the degree of entanglement increases past a critical point, geometry and temporal direction arise. Thus, the Big Bang becomes a shift in information topology, not a physical detonation. Even more intriguingly, some physicists speculate that entropy may hold the key to understanding what came before the Big Bang. Entropy, the measure of disorder or information in a system, tends to increase over time. In our universe, it's been rising ever since the Big Bang. But if entropy has a direction, then reversing it might imply a time-reversed universe on the other side of the singularity. In this mirror universe model, what we consider the beginning might be a symmetrical center. On one side, time flows forward, our side. On the other, time flows in reverse. It doesn't mean someone is living backward on the other side of the Big Bang, walking in reverse and unaging like a cosmic Benjamin Button. Instead, it implies a universe with opposite thermodynamic direction, where causes still precede effects, just in an opposite arrow of time. This twin universe, if it exists, could be the hidden half of a perfectly balanced reality. These reflections invite another radical idea. Maybe time is not fundamental at all. In some quantum gravity theories, time is an emergent phenomenon, much like temperature. Temperature is not fundamental. It arises from the motion of particles. Similarly, time might emerge from the entanglement structure of quantum states. This would mean that before the Big Bang might be a meaningless phrase, not because nothing existed, but because time didn't. Without time, there is no before. There is only a state, and then a transition. A timeless void condensing into a time-structured cosmos. In this view, the Big Bang becomes the emergence of time itself. Not the start of a movie, but the appearance of the projector. The notion of timelessness is also explored in the Wheeler-DeWitt equation. a mathematical attempt to combine quantum mechanics and general relativity. Strangely, this equation does not contain time as a variable. This leads to the so-called problem of time in physics. If the fundamental description of the universe doesn't involve time, then time may be a secondary derived concept, something our brains construct to make sense of change. So how did we get here? In a cosmos possibly birthed from timelessness. What makes us experience time at all? That might be where consciousness enters the frame. Our perception of time could be a result of entropy-driven processes in our brains. We create narratives of past, present, and future as a survival mechanism, but the universe itself may not care about time the way we do. It just is. We are the ones adding a soundtrack and editing cuts. On a more tangible level, astrophysical observations still give us clues, tiny variations in the cosmic microwave background, the distribution of galaxies, the absence of monopoles. Each detail confirms or challenges elements of our cosmological models. Every wobble in the data is like a footprint left in freshly fallen snow, hinting at something that passed by long ago. Or perhaps something that never truly left. Some experimental physicists even dream of creating miniature universes in particle accelerators. Not to destroy ours, but to study the conditions of the early universe in a controlled setting. If successful, such experiments might reveal whether space-time can nucleate under certain energy conditions. That would suggest the Big Bang isn't a singular event, but a reproducible phenomena under specific circumstances. Like baking a cake. If you happen to live inside an oven made of dark energy? But what about dark energy and dark matter? The things that fill 95% of the universe, yet elude direct detection. Could they be remnants from a prior universe? Could they be evidence of interactions with a meta-reality beyond our observable realm? These are questions scientists ponder as they look for signatures in gravitational lensing, in the spin of galaxies, in the alignment of large-scale structures. Some patterns suggest a preferred direction in the cosmos, a so-called axis of evil, which hints at large-scale anisotropies. If confirmed, such anomalies might challenge the assumption that the universe is isotropic and homogeneous. And if the universe is not uniform, then maybe it was born from a structured, pre-existing condition, not a pure, symmetric singularity. One final concept to consider is quantum cosmological determinism. This philosophical stance posits that all universes that can exist, do exist, and always have. Ours is simply a deterministic unfolding of initial quantum conditions with no true beginning or end. The Big Bang, in this view, is not a starting gun, but a local reconfiguration in a universal system that is eternally solving itself, like a multidimensional equation written in the margins of infinity. If that seems overwhelming, good, it should be. Because to ask what happened before the Big Bang is to ask about the structure of reality itself. And every answer we propose bends the boundaries of knowledge and language. But that's what makes the question so compelling. It's not a riddle with a clean solution. It's a doorway, and through it lies a horizon of infinite wonder and complexity. And the truth, if ever fully known, may not resemble a bang at all. It may be a whisper, a fluctuation, a slow unfolding, something that didn't start at all, but simply became. The tapestry of the cosmos is woven not just from particles and forces, but from questions, frayed edges in our understanding that flutter wildly in the winds of speculation. At the center of these is the one question we keep returning to, like a compass needle twitching toward magnetic north. What really happened before the Big Bang? And even more unsettling, did it happen at all? To chart the pre-Big Bang landscape, we must re-examine the notion of beginnings. In a purely Newtonian world, time extends infinitely in both directions, like a line without endpoints. But general relativity curves that line, sometimes bending it so tightly that it loops back on itself, and quantum mechanics. It pokes holes in the line, blurs its edges, and occasionally suggests the line was never the right metaphor to begin with. Instead, what we might be dealing with is something more like a quantum cloud of possibilities from which this specific universe condensed. Consider the idea that space-time itself could be an emergent phenomenon. Some physicists suggest that it arises from entanglement, a deeply quantum property where particles become linked, such that the state of one instantaneously affects the other, regardless of distance. If space-time is built from entanglement, then what we perceive as geometry, the curvature of space, the tick of time, could be an illusion born from relationships between information. In that case, before the Big Bang, there may have been no space to expand, no time to begin, only a primordial entanglement webbed with potential encoded within it. This perspective fundamentally alters the narrative, rather than the Big Bang as an explosion, or even as an inflationary event. It becomes a phase transition, a sudden reorganization in the deep quantum structure of reality. Just as ice melts into water or gas condenses into rain, perhaps our universe froze out of a hotter, more chaotic informational field. This phase change didn't occur in space and time. It generated space and time. To explore this further, we must plunge into the mathematics of background independence. This is a property of some physical theories where space-time isn't a fixed backdrop, but is shaped and defined by the fields and forces within it. General relativity is background independent. Quantum mechanics typically is not. This mismatch has haunted physicists for decades. To reconcile them, they seek a theory of quantum gravity, one that could describe how space and time behave when squeezed into incredibly small scales, like those just before or during the Big Bang. Among the contenders is loop quantum gravity, which discretizes space into tiny chunks called spin networks. Imagine the universe as a massive cosmic web made of loops and knots, where each node represents a quantum of space. Time, in this framework, is not a smooth flow, but a sequence of transitions between configurations of this network. The Big Bang, then, is not a singular moment, but a passage, a quantum jump in the configuration of the spin network. In this model, what lies before the bang is a previous configuration, perhaps a contracting universe that reached a critical density and rebounded. This leads us to the concept of the Big Bounce. Instead of a universe from nothing, we get a universe from something else, a prior cosmos collapsing, compressing, and then rebounding into a fresh expansion. The Big Bounce has appeal because it sidesteps the singularity, that mathematical point, where density and temperature become infinite and physics breaks down. Instead of surrendering to infinities, it proposes a cosmic reset. Previous cycles could stretch infinitely into the past, with each bounce erasing the memory of the last, save for faint imprints on the structure of space-time. But such ideas demand evidence. And evidence is a hard thing to find when it comes to something that occurred over 13 billion years ago, in conditions that leave few direct traces. One hopeful avenue is the cosmic microwave background (CMB), the faint glow of radiation left over from the early universe. Patterns in the CMB might reveal hints of events that occurred before inflation. Unusual alignments, low variance in temperature fluctuations, or subtle correlations could point toward a pre-Big Bang structure. But these interpretations are tricky. The data is noisy, and the signals, if they exist, are faint and ambiguous. Still, the search continues. Satellite missions, radio telescopes, gravitational wave observatories, all designed to push our observational reach a little closer to that hazy frontier. And while we may never fully see beyond the Big Bang, we might at least glimpse the fingerprints of whatever came before. One particularly adventurous hypothesis suggests that the Big Bang was not a solitary event, but part of a quantum birth process that happens repeatedly. This idea, called quantum cosmogenesis, treats the universe as a probabilistic outcome of a quantum system with a vast number of possible configurations. Most configurations do not yield a stable universe, but occasionally one does. In that rare moment, a universe like ours snaps into existence, unfolds, and evolves. The striking implication here is that the universe may not be unique. It may not even be rare. It could be one of an unfathomable number of attempts in a vast cosmic landscape. This dovetails with the idea of the string theory landscape, a collection of possible vacuum states, each corresponding to a universe with different physical laws and constants. In such a scenario, the Big Bang is simply the realization of one vacuum state out of many. But how does one vacuum state give rise to space and time? Again, we circle back to quantum tunneling, a vacuum fluctuation, a temporary, spontaneous change in energy might allow a region of false vacuum to decay into a lower energy state, releasing energy that manifests as space-time expansion. The process is similar to how radioactive elements decay or how particles appear in high-energy environments. The main difference is scale. This isn't a subatomic event, but one that seeds an entire universe. In these models, time doesn't precede the universe. It is born with it. Asking what came before is like asking what came before the rules that allow questions to exist. And yet, physicists persist in reframing the question, bending it until it fits the language of their mathematics and the boundaries of observation. Even classical general relativity, though it predicts a singularity at time zero, also suggests that singularities are not the end of the story. They are indicators that the theory breaks down. Beyond them lies a realm requiring a different description, likely quantum in nature, where probability, uncertainty, and non-locality dominate. It's in this quantum fog that we must look for the roots of our cosmos. But perhaps we're still framing the problem the wrong way. Maybe instead of asking what happened before, we should ask why there is something rather than nothing. That ancient question has puzzled philosophers and physicists alike. Could nothingness be unstable? Could existence be the default state? Or is non-existence itself a logical impossibility? Some argue that a true nothing cannot exist. Even a vacuum contains energy, fields, and potential. A state of absolute non-being may not be coherent within our physical framework. In that case, the Big Bang didn't arise from nothing. It emerged from a pre-existing reality that defies simple description. A realm where potential outweighs presence, and from which the universe emerged, not in an explosion, but as a whisper from the void. At this point, the line between physics and metaphysics grows razor thin. But rather than viewing this as a limitation, it may be a sign of progress. The fact that science is pushing against the walls of meaning itself suggests we're approaching a deeper level of understanding. In all these models, the cyclic, the bouncing, the quantum fluctuating, the holographic, one theme persists. The Big Bang is not the beginning. It is a threshold, a surface, a transformation. Like the crest of a wave, it may be spectacular, but it is built from hidden depths. Whether those depths contain another universe, a different phase of reality, or a web of timeless quantum logic, we do not yet know. But we are looking, always looking. The idea that the Big Bang may not have been the ultimate beginning forces us to reconsider what we mean by origin. An origin implies a fixed point, a first step, a definable event that sparked everything that followed. But when we examine the Big Bang through the lens of quantum cosmology, string theory, loop gravity, and other bold frameworks, we find that origin itself is a flexible concept, shifting, folding, and sometimes dissolving into the fabric it's supposed to explain. The deeper we look, the less the universe seems like a story with a first chapter, and more like a manuscript with no known beginning and possibly no end. Even the term Big Bang becomes something of a misnomer. It was coined by Fred Hoyle, ironically, as a sarcastic jab at a theory he didn't believe in. And yet, it stuck, becoming the label for what was never a bang and possibly not very big. It's difficult to change such names once they lodge into the collective imagination. But perhaps it's time. What happened roughly 13.8 billion years ago was more likely a smooth, expansive transition from an extremely hot, dense state into a universe governed by physical laws that permitted stars, galaxies, and eventually people who could misname cosmic events. So what if we stop asking what came before the Big Bang and instead ask what kind of reality allows the Big Bang to happen? This pivots the question from one about history to one about structure. And that's where we encounter the most ambitious proposals in theoretical physics, those that attempt to define the architecture of all possible universes. The idea of a multiverse continues to expand in conceptual scope. In the inflationary model, we have eternal inflation generating bubble universes. In the string theory landscape, we have a near infinite number of stable configurations of fundamental strings and branes. In quantum mechanics, we have the many worlds interpretation, in which every quantum decision spawns a new branch of reality. All of these models suggest that our universe is not alone and that what we experience as the Big Bang was a localized event within a much larger meta-reality. This leads to one of the most disorienting ideas in physics. Our universe may be one possible solution to a massive equation or a single point in a higher dimensional phase space. It may not even be particularly special. If there are infinite universes, then some will be chaotic, some will collapse quickly, and a rare few, like ours, will support complexity and life. This is sometimes called the anthropic principle. We observe the universe to be this way because if it were any different, we wouldn't be here to observe it. It sounds tautological, but it places us within a grand statistical framework. Statistical cosmology proposes that given enough possibilities, any configuration can and will emerge. But this raises difficult questions. Does probability require time? Can we have statistics without a sample space? And what does it mean for something to be likely or unlikely in a realm where causality may not even apply? To make progress, physicists have turned to information theory. In this approach, the fundamental unit is not matter, energy, or even space. It's information. Everything in the universe, from black holes to quarks to the expansion of galaxies, can be viewed as information being processed, transferred, and reorganized. In this sense, the universe may be a vast computation, unfolding over time according to algorithms we partially understand and partially suspect exist beyond our comprehension. This reframes the Big Bang as an informational event. Perhaps it marks a point of maximal entropy compression, a moment when information was at its most dense and undifferentiated, and from which all further complexity has evolved. Or perhaps it was the beginning of an informational resolution, as a low-definition quantum fog resolved into a high-definition universe. Some researchers have proposed that space-time itself arises from quantum entanglement. In this model, described through tensor networks and a ds-CFT duality, space-time geometry is not fundamental, but emerges from the connectivity of entangled quantum systems. The very shape of space could be a kind of illusion, an emergent property of deeper informational structures. This implies that before the Big Bang may refer to a phase where this entangled structure had not yet produced coherent geometry, where the raw data of the universe was stored but not yet compiled. At this point, the metaphor of a universe as a book becomes useful. The Big Bang is not the first word, but the moment when ink meets page. The story may have been written already, the ideas composed, the grammar outlined. The page, however, was blank until this universe began to unfold, and still, questions persist. Could there be signs embedded somewhere in the cosmic structure that tell us about this deeper framework? Perhaps subtle patterns in the arrangement of galaxies or in the polarization of the cosmic microwave background, or even in the way time itself seems to behave under extreme gravitational conditions. We are like cryptographers reading between the lines, looking for watermarks in the cosmos. The concept of time reversal symmetry in physics hints at something profound. In many fundamental equations, time runs both ways. Only when you zoom out to macroscopic scales and introduce entropy does time seem to have a direction. This opens the door to models where the Big Bang is the midpoint of a larger symmetry, two universes expanding in opposite temporal directions. Each would perceive itself as the forward-flowing one. The other, unreachable, would be its reflection, governed by the same laws but evolving in reverse. But how do you test something like that? How do you access a region of time flowing the other way? The answer may be, you don't. Yet it might explain why the total entropy of the multiverse is constant even while it increases locally in each universe. Two arrows of time diverging from a shared entropy origin. One of them led to us. The other could be filled with beings asking the same questions in mirrored words. There's also the question of scale. Our observable universe contains around 2 trillion galaxies, each with hundreds of billions of stars. Yet this may be just a speck in an unobservable greater whole. If our universe is spatially infinite, or if it wraps around in higher dimensions, then the Big Bang may not have created everything, just everything we can see. Other regions, inaccessible to us, may have entirely different histories, compositions, even dimensionalities. Some models suggest that new universes can be born from black holes. When matter collapses into a singularity, it may rebound into a baby universe on the other side of the event horizon. This provides a tantalizing feedback loop. Stars die, black holes form, and from those deaths, new universes emerge. The Big Bang could then be the exit wound of a black hole in another universe. This is sometimes called fecund universes theory, a cosmological cycle of birth through collapse. Even more speculative is the idea that intelligent life could eventually create universes. If advanced civilizations understand the mechanics of universe creation, say, by triggering certain quantum conditions or black hole dynamics, they might seed new universes with favorable laws. This turns cosmology into something almost evolutionary. Universes that generate intelligence might spawn more universes. Those that don't fade into silence. From this view, the Big Bang is not an isolated miracle, but part of an ongoing generational process. Our universe might be someone else's experiment or a link in an endless chain. And that makes the notion of a before both more mysterious and more mundane. So what really happened before the Big Bang? Maybe nothing, maybe everything. Maybe something we don't yet have the words or concepts to describe. But what we can say is this: the Big Bang, once considered the beginning, is now better understood as a boundary, one that marks the edge not of reality, but of our understanding. As our theories evolve, that edge recedes, and in chasing it, we uncover not just the universe's secrets, but something of our own nature, the insatiable curiosity that keeps asking what lies just beyond the visible, what sings behind the silence, what waits before the beginning. To ponder what lies before the Big Bang is to stand on the razor's edge of both physics and philosophy. It's a place where theories float free of empirical tethers and where speculation becomes a structured art form. Here, even the vocabulary of science starts to soften, its terms stretched and twisted to accommodate possibilities not yet observed, perhaps never observable. But despite this, the journey continues, driven by the hope that if we ask the right questions long enough, the universe might, in its own cryptic way, respond. One question that continues to haunt cosmologists is whether the Big Bang was a necessity or an accident. Was it the inevitable outcome of physical laws operating in a prior condition? Or was it the cosmological equivalent of a rare dice roll? Unlikely, unpredictable, but ultimately real. To answer that, we must look not only at physical theories, but at how they treat the concept of contingency. That is, could the universe have been different? And if so, why did it turn out this way? One compelling proposal that tries to answer this is known as the Hartle-Hawking state, or the no-boundary proposal. As mentioned earlier, it suggests that the universe didn't begin with a singularity, but emerged smoothly from a timeless, spaceless state. In mathematical terms, time behaves like a spatial dimension at the very beginning, meaning that the universe doesn't have a sharp starting point, but rather a rounded origin, like the South Pole of the Earth. From this model, the Big Bang is a quantum transition from a Euclidean timeless geometry to a Lorentzian time-involved geometry. In this phase shift, the fabric of the universe doesn't erupt from nothing, but gradually solidifies out of a quantum probability cloud. The geometry of space-time condenses like frost forming on a window pane. This gentle, borderless emergence bypasses the need for a before and after. There is only the shift. But where does this geometry come from? The mathematics used to describe it, quantum wave functions, path integrals, boundary conditions, suggest that the laws of physics themselves may be timeless. That is, the fundamental framework that allows universes to emerge may not require time to function. In that case, what we call the Big Bang is not a start in time, but a selection from a range of possible universes, chosen by the parameters of a quantum law that has no need for clocks. This hints at an even deeper idea, that the laws of physics may exist in a Platonic sense, outside of space and time, waiting to be realized. In this interpretation, the universe exists because the conditions allowed for it to exist, and those conditions themselves are rooted in logic and mathematics. It's not a satisfying answer to everyone, but it transforms the question from what happened before to why are the laws such that this could happen at all. Another interesting line of inquiry comes from causal set theory. This approach posits that space-time is not continuous, but built from discrete elements called events, each connected by cause and effect relationships. In this framework, the universe grows like a tree, with each new event sprouting from a set of previous ones. The passage of time is the growth of this network, and the Big Bang is merely the root node. Nothing special, just the first link in a vast causal structure. Causal set theory removes the need for a smooth beginning and replaces it with a granular genesis. It allows the possibility that something preceded the Big Bang, not in a classical sense, but in a prior set of causal events. Perhaps even another causal set from which our current universe sprouted like a bud from a branch. If true, this would imply that space and time are illusions emerging from deeper relationships. Not the foundation, but the facade. There's also the provocative idea that time itself may be cyclical, not just metaphorically, but physically. In this model, called conformal cyclic cosmology, the universe undergoes endless cycles of expansion and cooling. As it reaches a final, stretched-out state where particles decay and black holes evaporate, the universe becomes scale invariant, meaning it no longer has any meaningful sizes. At this point, the geometry becomes mathematically identical to the ultra-dense, hot beginning of a new universe. The end maps seamlessly onto the beginning. One eon ends, another begins, in a continuous chain. This concept is radical because it means the Big Bang is not a singular moment, but a bridge between cycles. And if we could identify patterns from a previous eon in our current cosmic microwave background, like circular imprints from supermassive black holes in a prior universe, we might, in theory, find physical evidence of events that happened before our universe began. Although these claims are controversial and hotly debated, the pursuit is ongoing, and the implications are profound. Such theories challenge the linear conception of time that dominates our thinking. We prefer stories with beginnings, middles, and ends. But the universe may be a loop, a spiral, a kaleidoscope of rebirths with no true start or finish. If so, the Big Bang is a page turn, not a prologue. Other models avoid time entirely by returning to the realm of pure quantum mechanics. One approach treats the entire universe as a quantum state evolving according to a wave function. In this model, all possible histories of the universe exist simultaneously, like overlapping echoes in a cathedral. The Big Bang isn't a moment, it's a dominant solution in the universal wave function. What we perceive as time and sequence is a projection of our local experience within one path of this function. This idea, known as the quantum multiverse, suggests that every possible history happens. The reason we see this particular version is that we are part of it. Other versions include different physical laws, different constants, even different space-time structures. There's no way to leap between these histories, but they coexist in a vast mathematical reality that dwarfs anything we can observe. Still, this leads us back to one inescapable feature: the extraordinary fine-tuning of our universe. The physical constants, the relative strengths of forces, the balance of matter and energy, all seem tuned precisely to allow complex structures, chemistry, and eventually life. If these values had been slightly different, stars wouldn't form, atoms wouldn't bind, and no one would be here to ask these questions. Does this mean our universe was designed? Not necessarily. In a multiverse of infinite variety, most universes are sterile, lifeless, unstable. Ours happens to be one of the rare ones that works. That's not design, it's selection bias. Where? The lottery winners asking why we got the ticket. This view, known as the anthropic principle, isn't universally loved. Critics say it's unscientific, untestable, even defeatist. But it may be the most honest way to explain the peculiar generosity of the cosmos. The Big Bang gave us a universe that could think about itself. That alone makes it an astonishing outcome, no matter what came before. Perhaps the answer is that there is no single answer. The pre-Big Bang cosmos may be a mystery with multiple valid frameworks, each providing different insights, like a mountain. Viewed from different angles, it reveals new features depending on your vantage. Some climb through quantum fields, others ascend through geometry. Still others float on thermodynamics or dive through information theory. And all are chasing the same invisible summit. The truth may be that reality doesn't lend itself to our need for singular narratives. It's not a novel, but a fractal, complex at every level, self-similar across scales, and never quite complete. In that case, the Big Bang is a pattern. A node, a point of symmetry within a cosmic architecture that defies chronology. Yet here we are, shaped by that moment, asking questions it made possible. If the universe emerged from nothing, or from a prior state, or from logic itself, it brought with it the capacity to wonder. That may be the most poetic legacy of all. The further we descend into the conceptual depths of what may have preceded the Big Bang, the more the lines between the empirical and the abstract blur into vapor. Physics, normally grounded in the testable and repeatable, finds itself suspended in the unobservable and possibly unknowable. And yet, theorists continue to excavate, searching for a signal amid the static, a whisper beneath the blast. One trail that refuses to fade is the hypothesis that black holes and the Big Bang are intimately connected, not just in their extremity, but perhaps in their identity. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. It is bounded by an event horizon beyond which all paths curve inward, toward a central singularity. That singularity resembles, at least mathematically, the singularity at the beginning of our universe. The two are cousins in the equations of general relativity. So, consider this. Might our Big Bang be the interior of a black hole formed in another universe? A collapsing star elsewhere in a greater cosmological structure could form a black hole, and inside that black hole, space and time could re-emerge, expanding into a new, isolated universe. From the outside, it looks like a collapse. From the inside, it feels like a bang. This proposal, often called the black hole cosmology model, elegantly flips our perspective. Every black hole could spawn a baby universe. Perhaps even every black hole in our own universe has done so. We, in turn, may have emerged from such a cosmic womb. And if so, it raises fascinating questions about inheritance. Could fundamental constants be passed down like genetic traits? Could universes with stable physics create more black holes and therefore more universes, perpetuating a kind of cosmic evolution? This idea, known as cosmological natural selection, casts the multiverse in Darwinian light. Universes that are good at making black holes replicate. Those that are not, do not. Over time, the multiverse becomes populated with universes tuned for maximum black hole production. Intriguingly, a universe that makes many black holes also tends to support complex chemistry, stellar life cycles, and perhaps life itself. We may not be here despite this evolutionary trend. We may be here because of it. Yet again, we return to a motif that repeats like a fractal, the notion that the Big Bang is not a true beginning, but a transformation, a translation, an unfolding of a deeper state into a form we can measure and marvel at. The more models we examine, the less likely it seems that there was a moment of absolute nothing giving way to something. Rather, it appears that the conditions of our universe were drawn from an already existing realm, be it a prior universe, a quantum state, a parent black hole, or a timeless informational field. But suppose for a moment we return to the question of nothing, not as a void, but as a physical concept. Can nothing truly exist? In quantum field theory, even a perfect vacuum is filled with fluctuating energy, virtual particles popping in and out of being. The so-called vacuum state isn't nothing, it's teeming with potential. This leads some physicists to argue that true nothingness is not only physically meaningless, but also philosophically incoherent. You cannot have a reality where there are no laws, no time, no possibility. Even the absence of being must be governed by the rules that define what absence is. This makes nothing unstable. It cannot remain nothing. From even the tiniest nudge, a quantum fluctuation, a broken symmetry, something begins to crystallize. In this view, the Big Bang was not a cosmic act of creation, but a transition from instability to structure. Nothing gave way to something, not by force, but by necessity. The philosopher might say that being is more natural than non-being. The physicist might say that a quantum vacuum is more stable with structure than without. And so the bang occurred, not with a motive, but because the configuration we now call the universe was energetically favorable. This kind of reasoning dovetails with another idea, the spontaneous nucleation of a universe from a false vacuum. In some inflationary models, the early universe existed in a high-energy state, like a ball perched precariously at the top of a hill. That state is called a false vacuum. It's metastable, not quite at rest, but stable enough to persist for a while. Eventually, a fluctuation sends the system rolling into a lower energy state, releasing vast amounts of energy and inflating into a universe. In this framework, the Big Bang is a vacuum decay event, a kind of energetic collapse. The pre-Big Bang era was a sea of false vacuum, flat and featureless. Then, suddenly, one region fell, expanded, and cooled into a universe like ours. The geometry, the laws of physics, the particles and forces, all encoded in how that decay occurred, Other regions may have decayed differently, giving rise to other universes with other rules. This casts the multiverse as a patchwork quilt of bubble universes, each born from a vacuum fluctuation, each expanding into its own domain. Our observable cosmos is just one patch in an infinite fabric. Still, many cosmologists remain grounded in the observable, reluctant to commit to universes we can never see. They focus instead on what can be inferred from the CMB, the distribution of matter, the flow of time. And here, the data continues to whisper about early conditions. One feature of particular interest is the uniformity of the cosmic microwave. Background. It's remarkably smooth across vast distances, which implies that regions of the early universe were in causal contact. That is, they influenced each other. Standard Big Bang cosmology. Those regions should have been too far apart to interact before the light from the CMB was released. Inflation solves this problem by positing a brief, rapid expansion that allowed these regions to communicate before being stretched beyond each other's horizons. But if inflation occurred, it suggests a pre-inflationary state. And if inflation can happen once, it can happen again and again. And so we return once more to the concept of eternal inflation and the spawning of universes without end. Here, the Big Bang becomes a local event, a rising bubble in a vast champagne of cosmic foam. The broader space, sometimes called the inflating multiverse, never stops. It grows eternally, producing universe after universe. The Big Bang is no more a beginning than the birth of a snowflake is the start of winter. It's a sobering thought, but also a liberating one. If reality is vast beyond imagining, if beginnings are local rather than absolute, then our universe, our patch of space and time, is a unique and valuable expression, but not the whole story. What does this mean for us, wandering apes on a rocky planet circling a middling star? Perhaps nothing. Perhaps everything. Our minds, shaped by evolutionary pressures to spot patterns and infer causes, may never fully grasp the pre-Big Bang reality. But the effort itself matters. The act of wondering, modeling, questioning, these are our connection to the cosmos. They are how we participate in its story. In contemplating what came before the Big Bang, we aren't merely seeking data. We're expressing a deeper drive to place ourselves in context, to know where we came from, even if the answer is stranger than we can imagine. And so we continue. We invent models, build instruments, run simulations, revise theories. Each time we peer deeper, we find not emptiness, but structure, not silence, but possibility. Whether the Big Bang was a bounce, a birth, a transition, or an illusion, it gave rise to a universe that asks questions. In the end, maybe that's the real beginning, not the bang itself, but the first moment when the universe, through beings like us, began to ask what it was. If we allow ourselves to believe that the Big Bang wasn't truly the beginning, but merely a localized event in a much larger, older, or deeper cosmic process, then we are left with a profound responsibility to ask better questions, though nature of the cosmos may not reward us with simple answers. Instead, it may stretch our concepts of reality, fracture our definitions of time, and quietly suggest that everything we think is fundamental is actually emergent. The laws, the constants, even the geometry of spacetime, these may be shadows, cast by a deeper truth. And if that is so, then the moment before the Big Bang, if one can call it that, was not an instant of creation, but an aperture opening onto existence as we know it. To reach further, we might look again at a concept that straddles the boundary between physics and metaphysics. Dimensionality. The universe we experience has 3 spatial dimensions and 1 temporal dimension. But some theories, especially those from string theory and in theory, posit that additional spatial dimensions exist. Hidden, compactified, curled up so tightly that we cannot detect them with current instruments. These extra dimensions might hold the key to understanding pre-Big Bang conditions. In higher dimensional cosmology, the observable universe could be a three-dimensional brane embedded in a higher dimensional bulk. According to Brane World scenarios, our universe may have come into being, not from a singular explosion, but from a collision between two such branes. Like rippling sheets in a cosmic wind, branes can collide, merge, and rebound. The energy released in such an encounter could produce conditions indistinguishable from those of a traditional Big Bang. This is the basis of the ekpyrotic universe model, a name drawn from the ancient Greek term for conflagration. It proposes that our universe began with a brane collision in a five-dimensional universe, unlike the abrupt, singular origin of standard Big Bang theory. This model paints a picture of gentle convergence followed by violent rebirth. Time didn't begin. It merely continued through a cyclical dance of dimensions. Even more radical versions of this model allow for the possibility that these collisions are periodic. That is, they happen over and over again, each time spawning a new universe with fresh initial conditions. This creates a cosmology, not of one beginning, but of eternal cycles, each new universe born from the embers of the last. This naturally leads to a question. If universes are cyclical, do they retain memory? Do constants carry over? Do certain patterns repeat? The answer is unknown. But some scientists speculate that if there is any crossover from one cycle to the next, it might be found in the statistical irregularities in the cosmic microwave background. These patterns could act like cosmic fossils, the faint imprints of a universe long since collapsed or collided out of existence. But the pursuit of evidence is complicated by the fact that the CMB is our observational wall. It is the oldest light we can detect, emitted when the universe was only about 380,000 years old. Before that time, the universe was opaque to photons, like a fog too thick for light to pass through. We can infer what happened in the first few seconds, even fractions of a second, through models and particle physics. But the moment before that, it disappears behind a veil of unobservability. This hasn't stopped theorists from attempting to model the pre-CMB epoch. Some researchers are working with primordial gravitational waves, ripples in space-time itself, produced in the early universe. These waves, unlike photons, can pass through the fog of the early universe. If detected, they could provide direct evidence of inflation or even pre-inflationary physics. To detect such waves, experiments like the Laser Interferometer Space Antenna, LISA, and next-generation cosmic observatories are being developed. These tools may one day allow us to see through the fog to the other side of the so-called curtain. But what we might see remains speculative. Let us consider again the notion of a universe emerging from a quantum vacuum. This concept hinges on the idea that the universe is fundamentally quantum mechanical. That is, it doesn't behave like a deterministic machine, but rather like a probabilistic field of possibilities. In this picture, the Big Bang was not inevitable. It was one possible outcome among many, selected not by will or design, but by quantum fluctuation. These fluctuations are described by the Heisenberg uncertainty principle, which tells us that, even in a vacuum, energy and matter can temporarily exist, so long as they annihilate quickly enough. Over vast timescales, such fluctuations might become stable, nucleating into full-fledged universes. This is sometimes called quantum tunneling, and it's an idea with deep implications. It suggests that reality doesn't require cause in the traditional sense. It only requires permission, defined by the rules of quantum mechanics. In that sense, before the Big Bang is a field of fluctuating potential, not nothing, not something, but a liminal state where being and non-being blur, where the difference between real and virtual dissolves into the probabilities of the wave function. Our universe, then, is a realization of that function, a peak in the graph of what could be. In this framework, reality doesn't begin or end. It transitions, it reorganizes, it transforms. And what we call the Big Bang is not a rupture, but a reshuffling, one configuration giving way to another. The physics change, the dimensions bloom. The laws arise like frost from cooling glass. But the underlying reality, the substrate of quantum logic, remains untouched. And yet, even as we swim in theory, we must acknowledge that none of this is proven. The pre-Big Bang remains speculative territory. The models are elegant. The mathematics is persuasive. But the evidence is elusive. This is the frontier of human thought, not the limit of our ability, but the edge of what our instruments can detect. Still, history tells us that today's speculation is often tomorrow's insight. Once, the expansion of the universe was an untested idea. Once, black holes were theoretical curiosities. Once, even atoms were controversial. Science moves slowly at this scale, but it moves. And so we are left with many visions of the cosmos. In one, the universe emerged from a quantum fluctuation. In another, it arose from a brane collision. In yet another, it bounced from a prior contraction. Each model paints a different picture. Each has its merits. Each awaits its evidence. But perhaps the greatest lesson of this intellectual adventure is not a specific answer, but a broader perspective. To contemplate what came before. The Big Bang is to confront our own limitations, not just of technology or mathematics, but of imagination. It asks us to build castles out of abstraction, to engineer meaning in a place where time itself may not exist. And in that effort, we find something deeply human. A desire to know, not because we must, but because we can. A drive to reach backward into the darkness, hoping to touch the hand of whatever set the stars in motion. So what happened before the Big Bang? The answers range from bold theories to silent ignorance. But the question itself may be the most profound artifact of all, the echo of a thinking universe trying to understand its own birth. In the persistent search for what may have existed before the Big Bang, we find ourselves increasingly drawn, not only to physics, but to the architecture of thought itself. Every hypothesis, every equation, every simulated universe is built atop layers of assumptions about causality, about time, about the very rules that govern existence. We are not just exploring what lies behind the cosmic curtain, we are questioning the fabric of the curtain, the nature of space through which it might have moved, and even the meaning of behind when space itself may not have existed. This is where cosmology begins to reflect inward, folding onto itself like the very space-time it tries to describe. Theories become recursive. Questions about origins circle back into themselves. And yet, for all this intellectual curvature, progress is made. One conceptual advance comes from the idea that the Big Bang wasn't a temporal beginning, but a boundary condition. A point where our mathematical models reverse or become undefined, not because something happened, but because our language breaks down. This invites a new approach. Maybe the origin of the universe can't be explained by what came before in time, but only by the kind of state that makes time possible. In other words, time is not a backdrop, but a product. This idea finds support in the field of emergent spacetime. Here, time and space are not fundamental, but arise from deeper quantum informational principles. Entanglement, for instance, may stitch space together, and the flow of information may create the illusion of temporal sequence. In this view, the Big Bang isn't the start of time. It's the moment when time emerges from timelessness. A phase. Shift, a condensation of information into directionality. Such concepts challenge our intuitions. We're used to thinking of time as linear, universal, and absolute. But every major development in physics has undercut that idea. Einstein's relativity showed that time is local and variable, affected by motion and gravity. Quantum mechanics suggests that events are probabilistic and time-symmetric at small scales. Put together, these ideas hint that time, as we know it, is a kind of approximation valid for human-scale phenomena, but not universal. If time is emergent, then before the Big Bang may be as meaningless as north of the North Pole. It's a nonsensical question, not because the answer is hidden, but because the framework that allows the question to make sense didn't yet exist. This doesn't mean that nothing happened, only that the sequence of events is no longer a useful concept. To make this more concrete, imagine a simulation. A computer program may generate a virtual world with time, space, particles, and laws. But those things only exist once the program runs. Before that, there are only code and instructions, no sequence, no causality. Our universe, in this analogy, may be the runtime of a deeper informational process. The Big Bang is when the program begins executing, not because something pressed start, but because the conditions of execution became viable. Now, whether such a substrate exists or whether it makes sense to speak of it is up for debate. But it reframes the origin story in useful ways. Instead of a bang, we have a boot up. Instead of a singularity, a system call. And if the universe is information in motion, then the birth of our cosmos is not about matter appearing, but about relationships forming. In that light, consider another model, the holographic principle, originally developed from black hole thermodynamics. This principle suggests that the information contained in a volume of space can be fully described by a theory operating on its boundary. In other words, our three-dimensional world could be a projection from a two-dimensional surface. Like a hologram, the volume is real, but the information lies on the edges. If true, this means that the Big Bang, the expanding fireball we visualize in cosmic diagrams, may not be a central event, but a peripheral one. The universe's evolution could be a kind of unfolding from a lower dimensional structure. What we call the beginning may simply be the edge of this unfolding, the first ripple of projection. This leads to speculation about what kind of physics could exist on that boundary. Some have suggested that quantum field theories defined on the boundary could give rise to gravity and space-time in the bulk. This is known as the ADS-CFT correspondence, a deep connection between conformal field theories and anti-de Sitter spaces. While our universe is not an ad space, the mathematical insights from this duality are expanding our understanding of how space, time, and gravity may emerge from more fundamental ingredients. And once again, we arrive at a place where the Big Bang is no longer an isolated moment, but part of a network of interrelations, a convergence of boundaries, symmetries, and phase changes. A place where concepts like before and after may simply dissolve, but the human mind is tenacious. We continue to seek narratives because we are creatures built from time. We remember, we anticipate, we sequence. Even when nature shrugs at chronology, we cannot. So let's take a final detour into one of the most provocative ideas yet, that our universe is not a primary entity, but a simulation. This idea, though often treated as science fiction, has gained serious traction in philosophical and scientific circles. The basic logic is unsettlingly simple. If intelligent civilizations eventually gain the ability to simulate universes with conscious agents, and if they create many such simulations, then simulated universes could vastly outnumber real ones. Therefore, by the laws of probability, we might ourselves be living in one. What does this mean for the Big Bang? In a simulation framework, the Big Bang might be a deliberate construct, a parameter setting, an initialization routine. It's not an explosion, but a load event. The laws of physics are code. Constants are configuration files. The before the Big Bang, in this context, is whatever exists outside the simulation, on a server, in a reality with different rules. This notion opens up a Pandora's box of implications. If the universe is a simulation, can it be modified? Is there an observer? Are there limits to computation, pixels of space, frames of time, glitches? While fascinating, these questions currently lie beyond testability. But, like other theories of the pre-Big Bang era, they challenge us to reconsider what we mean by reality. And yet, perhaps this is the core revelation of all these explorations, that the Big Bang is not simply a historical question, but a mirror reflecting our deepest assumptions. Whether we see it as a birth, a bounce, a bubble, or a boot up, we are ultimately asking about ourselves, our place, our moment, our meaning. For in the end, the universe doesn't ask to be understood, it simply is. But we, small fragments of cosmic dust, have evolved minds capable of turning inward, outward, and backward through time. We imagine, we calculate, we dream. The Big Bang may never yield a single answer, but the act of asking, of building models, conducting experiments, refining thought has already reshaped our understanding of reality in ways that no single theory ever could. And so we stand here, at the precipice of knowledge, peering into the fog of beginnings. We may never know what came before, but we can know what such curiosity says about us. There's a certain irony in how the search for what came before the Big Bang continually brings us back to ourselves. The more we peer into the deep unknown, into regions where space, time, and cause may lose all meaning, the more we find that the questions we ask are shaped by our own limitations. The mind that dares to imagine a time before time, a state before space, a cause before causality, is itself a product of a universe already in motion. The light from the Big Bang has cooled into microwave background radiation, but our need to chase its origin still burns with cosmic intensity. In the final sweep of current thought, one begins to understand that the Big Bang might not represent the first page of the universe, but merely the first chapter that we are capable of reading. Every model we have, no matter how exotic or elegant, runs up against a boundary. For inflationary models, it's the pre-inflationary state. For string theories, it's the physics of the extra dimensions. For loop quantum cosmology, it's the bounce from a previously contracting universe. For conformal cyclic cosmology, it's the stretching out of the previous eon. For the quantum universe, it's the shape and interpretation of the wave function. For brane collisions, it's the dynamics of higher dimensional membranes in a bulk space. For all of them, it's the moment when time becomes meaningful or loses meaning altogether. It is fitting, then, that the edge of physics feels more like poetry than prose. Consider a model in which the universe is fundamentally timeless, and time as we experience it is a derived quantity, an emergent phenomenon. The conditions that gave rise to the Big Bang, if such a phrase even holds, were neither before nor after anything. They simply are. Timeless, formless. They gave birth not just to matter, but to the very logic by which we structure our thoughts. If time began at the Big Bang, so did meaning itself. The laws of thermodynamics, the equations of motion, the constants of nature, none of them existed in any practical sense until there was a framework for measurement, change, and interaction. And yet still we ask. Still we want to know if there was a cradle beyond the cosmic dawn, a whisper beneath the cosmic roar. Perhaps this is why simulation theories, holographic universes, and informational cosmologies are not so far-fetched after all. They shift the focus away from matter and energy and onto logic and structure. They suggest that what underlies reality may be mathematical, not material. Some cosmologists have even gone further, proposing that mathematics itself is the only real thing. In this view, known as mathematical Platonism, The universe exists because the equations that describe it are timelessly true. Reality is a structure of relations, pure, abstract, and necessary. In this case, the Big Bang is not a physical event, but a node in a vast network of mathematical truth. It didn't happen so much as it is, in the same way that the Pythagorean theorem is always true, regardless of whether anyone observes it. Whether one finds comfort or disquiet in this view is a matter of temperament. Some see beauty in a cosmos that emerges from logic alone. Others crave a more tangible narrative, heat, motion, compression, expansion. But in either case, we are left with a truth that transcends physics. Our desire to explain our origins is itself part of the universe's unfolding. The question is not external to the process. It is the process. Every equation, every telescope image, every bold hypothesis is another ripple in the expanding mental cosmos of our species. And what if we never find the answer? What if the pre-Big Bang realm, whatever it was, remains forever out of reach? Masked by the limits of observation, blurred by the uncertainty of quantum fluctuation, or concealed behind a fundamental limit of knowledge? Would that be defeat? Or simply the natural boundary of a self-aware universe, forever marveling at its own improbability? Perhaps we are not meant to know everything. Perhaps reality is not a puzzle to be solved, but a canvas to be appreciated. The Big Bang in this light is not a problem. It is a poem, a metaphor written in plasma and light. An opening stanza. In the greatest epic ever conceived, even if we could wind back the cosmic clock, past the formation of galaxies, past the birth of stars, past the searing glow of recombination, past inflation, past the Planck epoch, we might still find the pre-Big Bang state to be indistinct. Not because it is blank, but because it is everything. A quantum fog, a sea of potential, a condition without conditions, a truth without time. But then again, who are we to say what is impossible? The history of science is a parade of impossibilities. Overturned black holes were once absurd. Quantum tunneling was once magic. Cosmic expansion was once nonsense. Time and again, the universe has revealed itself to be stranger than our best guesses. Why should the origin of time be any less extraordinary? In that spirit, the inquiry continues. Data accumulates. Models evolve. New instruments hum to life. In mountaintop observatories and satellite laboratories, the conversation deepens. With every generation of scientists, the event horizon of understanding is pushed further outward, or perhaps inward. The Big Bang is no longer a single point in space or time. It is a landscape of ideas, a challenge to meaning itself. So what really happened before the Big Bang? Maybe there was a bounce, maybe a brain collision, maybe a timeless state of quantum logic, maybe a field of mathematical inevitability, maybe a failed vacuum, maybe a computational birth. Or maybe the question will never be fully answered. Maybe it's meant to be asked again and again, not because it has a solution, but because it opens the doors of wonder wider than anything else in science. In the end, the Big Bang gave us more than space, time, and matter. It gave us the capacity to wonder, to doubt, to dream of explanations that stretch the limits of what minds can hold. And perhaps that, more than any theory, is what truly came. First, the possibility of asking. Thank you for watching this exploration from the Slow Science Sleep channel. I hope this journey through the unimaginable edges of time and existence has both engaged and, somehow, helped you rest. If, however, it made your mind spin instead of slow down, if these thoughts have chased sleep from your eyes, then I sincerely apologize. Please remember to like the video, subscribe to the channel, and leave a comment below, sharing where you're watching from and what time it is there. Every shared curiosity connects us in this strange, expanding universe. And now, I invite you to drift gently into the ambient sounds that follow. Let them carry you past galaxies and particles, past bounces and beginnings, past the limits of thought, into a space where wonder has no edge. Good night.